Hi, this is Professor Fernandez. In this video, we are going to work on telescoping series and specifically determining if they converge or diverge. This example we're going to work on comes from lesson 6 in this Calculus 2 course. If you want to take a look at the lesson or download other goodies for the course, head over to that site. You'll find all those lecture notes, practice problems, and a bunch of other stuff there. So let's take a look at the example. I'll zoom in here. Determine whether the following telescoping series converge. So telescoping series, we talked about that in a previous video and also in the notes, but long story short, what is a telescoping series, right? It's a series that has the form A1 minus A2 plus A2 minus A3 plus A3 minus A4, and so on. So in other words, there's the first term in the series has as its last term the same as the first part of the second term. It's much easier to see this written out than it is to talk about it. What results from a telescoping series is what you can kind of see if you start working out the partial sums here. A2 here is going to cancel with that one. A3 here is going to cancel with that one, right? So if you work out the partial sum S sub n for a telescoping series, it's going to be the first term minus A sub n plus 1. So this is really good because, like we talked about in an earlier video and also earlier in this course, the limit as n goes to infinity of the partial sums, this is really literally what we mean by this, right? The infinite series going all the way to infinity. And therefore, if this S sub n is given by A1 minus A sub n plus 1, A1 doesn't go anywhere as n goes to infinity. That stays A1. So I'm left evaluating this limit. So in a telescoping series, because this is the formula for S sub n, once you figure that out, right, it really all depends on A sub n plus 1, whatever formula that is. If that limit as n goes to infinity of that A sub n plus 1 is a number, exists, equals some number L, then the infinite series converges. And, right, we can say that the sum of the series is in fact this. And that's really nice, right? We've seen geometric series in the course, and we can find the explicit sum for those. Telescoping series now is another category of series, or type of series, where we can find the explicit sum. Okay, I'm just going to let you pause the video for a minute and read this over. If you're interested, this says pretty much exactly what I just said, but in theorem form. So again, takeaway, first of all, you have to realize that all of this is only for telescoping series. So there is the skill of being able to spot a telescoping series. I'll talk about that in a minute. But then also, whether or not the telescoping series converges or diverges comes down to the limit of that A sub n plus 1 term. All right, so let's go through the example. All right, so all of this says determine which of the following telescoping series converge. So I'm already telling you it's a telescoping series. If you didn't know, how would you be able to tell? Just zooming out, you can kind of see visually how you can spot the series, right? Here's cosine n, here's cosine n plus 1, and they're being subtracted. So that's a telltale sign of a telescoping series. You have the same function being subtracted, and then whatever the argument or whatever, however you want to call it, whatever term is here is, and the n plus 1 version of it is here. Same thing over here, right? Here is 2 over 3 to the n, 2 over the power of 3, and this one has an n. This was the next one, n plus 1. Same deal here. This one looks different, and we'll get there, but you'll see that when we do some algebraic manipulations, it'll fit the pattern I just described. Great, so even if you didn't know that beforehand that these are telescoping series, if I just didn't tell you that, right, then at least now you have some way to perhaps figure out that they are a telescoping series. So now we move on to determining convergence, divergence. We have our nth partial sum, right? That's A sub 1, right, or whatever the starting value of the series is. It's 1, 1 for all of these series here, 1, 1. So we have our S sub n, A sub 1, minus A sub n plus 1. Okay. So what is A sub 1 in this case? It is cosine of 1. And what is A sub n plus 1? Well, so that's going to be cosine of n plus 1. Okay, so a sub the a's I'm referring to here, these an's, right, are literally just what you get from the infinite series, right? If you're ever in doubt, you can write out the infinite series itself. The first term here would be cosine of 1 minus cosine of 2. Second term would be cosine of 2 minus cosine of 3. And then again, just as a way of reviewing some of this partial sum stuff, the first partial sum is cosine of 1 minus cosine of 2. The second partial sum is that one plus this one, which is where you start seeing the cancellations. So that's just cosine of 1 minus cosine of 3. And then you start seeing this phenomena, right? S1 has cosine of 1, S2 has cosine of 1. That term is always in there. And then S1 has minus cosine 2, S2 has minus cosine 3. So Sn has minus cosine n plus 1. Okay, so a quick little review there of how this works for telescoping series. So back to the example, I have Sn, there it is, and I now want to figure out what is the limit as n goes to infinity of Sn. Again, we already figured out that the a1 term just goes along for the ride, right? It doesn't go anywhere as n goes to infinity because it doesn't have an n in it. So I'm really just calculating, evaluating the limit as n goes to infinity of this particular function. This is kind of like an example we've done before. Cosine of n plus 1, it just oscillates, right, as cosine does forever. So this limit does not exist, right? So my final answer here is dne. I'm not going to write equals, I'll just say dne. So I guess I'll tell you what dne's, what does not exist. So the limit as n goes to infinity of s sub n does not exist. So what does that tell us? Well, here I will go back to the fact that, remember that the infinite series 1 to infinity an is the limit of the nth partial sums. So if this limit does not exist, then the infinite series diverges, right? So that was part of our definition of what it means for a series to diverge or converge. So determine which of the following series converge, right? Definitely not this one, first one we worked on. So this one diverges. Okay, so moving on to part B here. What are we going to do for this one? Same deal, right? So if I write out S sub n, that's going to be the first term, the first part of the first term, the a1 term. That's this part for n equals 1, that's 2/3, minus a sub n plus 1. So that same thing, but I substitute in capital N plus 1. Okay, so doing the limit analysis here as n goes to infinity of Sn, this part stays 2/3, and then I'm left evaluating this limit. And then back to all the sort of different techniques you could apply that we've been talking about. Here I have an exponential function in the denominator, and I have this same 2, right? No matter what capital N equals, it's always 2 in the numerator. So this is going to tend to 2 divided by some giant number, which tends to 0. So I was subtracting 2/3, so my conclusion is that the limit as n goes to infinity of Sn equals 2/3. Okay, so now I did get a number, so therefore my original sum, which is up here, this telescoping series, my original series not only converges, actually it converges to the limit that I got of the partial sums, right? 2/3. So it converges to 2/3. All right, so that is pretty cool. So I've gotten convergence now for part B. I'm going to move on then to part C, erase some of this stuff, get some more space for us here. Okay, so part C, what does this one say? So this is kind of a silly series, but I put it here for a reason. Look at what the series is, right? If I do some algebraic manipulation, it's n minus n plus 1. I distribute the minus, and I get this, so I get -1. So the series is 1 to infinity of -1, which is -1 plus -1 plus -1 plus. This is going to diverge, right? You're just always subtracting 1, so it's definitely not tending to any number. So we could do this series convergence divergence using, for example, the divergence test, right? That was a thing we covered in the previous video in lesson 5, I believe. That would show the series diverges. But as written, it is a telescoping series. So the point of me putting this example in this way in here and talking about everything I just talked about is to, again, give you different options and perspectives, right? Just because a series is a telescoping series or you're told that it's a telescoping series doesn't necessarily mean you have to analyze it that way. Obviously, unless you're told to or you're doing an exam or something. But that being said, if you have options, right, use, and this is something we're going to come to throughout the course, use those options, right? If you have different tests you can apply, think about which test is most straightforward, easiest for you to apply. But again, if we were doing this using telescoping series, S sub n would be the first term, which is 1, first part of the first term, minus, and then just put n plus 1 there. And here you can see pretty clearly that as n goes to infinity, right, I get 1 minus, and then this, like, basically is infinity. In other words, this limit does not exist, right? So the limit does not exist. The series does not converge. The series diverges. So diverges. Okay, so we got 2 divergence, 1 convergence. Let's see what's going to happen with this last one. I mentioned earlier that this was going to be an example that we would have to do some algebraic manipulation to fit into the telescoping series mold. So here we are. So what's the algebraic simplification? Remember the rules of logarithms, that ln of a over b is ln of a minus ln of b. So that's the property we're going to use here. So this series can be rewritten as ln of n minus ln of n plus 1. Okay. So now we can see its telescoping series nature. And that makes it easier for us to write down Sn. So it's the first part of the first term, ln at the starting value of n, ln of 1, minus ln of capital N plus 1. You might remember that ln of 1 is 0, right? So that's 0 minus ln of capital N plus 1. So in finding the limit as capital N goes to infinity of Sn, we are finding the limit as capital N goes to infinity of ln of capital N plus 1. Okay, so various ways to do this one, right? You could think of the graph of ln, looks like that, and then you could multiply it by a negative 1, it does that. And then you could think of just going that way forever. So ln of n plus 1 with a negative sign in front of it just decreases on forever, right? So this tends to negative infinity, which does not exist. Okay, so that tells us that this series diverges because its limit for its nth partial sums does not exist. So zooming out here, we got, oops, maybe I should put it in the same color to be slightly more consistent. There we go. So we got 3 divergence, 1 convergence. But again, 2 things to take away here. Number 1, if you're not told it's a telescoping series, right, the way to figure it out is perhaps to write out the first few terms like we did earlier over here, and then see if those kind of, the last part of the first term cancels with the first part of the second term, and so on and so forth, right? Then you got a telescoping series on your hands. If you do, then this theorem comes in really handy. The nth partial sum is like A1, where this is the first part of the first term, minus the n plus 1 version of that. And then finding the limit as n goes to infinity, if you get a number like we did over here, then it converges, right? The series converges to that, and that is its sum, right? It quote adds to that. I say quote because we define the sum of an infinite series to be the limit of its nth partial sum. If you get anything other than a number for this limit as n goes to infinity of the partial sums, if you get does not exist, if it tends to infinity, which is a version of does not exist, then the series diverges. That's what happened here, here, and also here. Thanks for watching.